Before we ever set foot on the moon, before we built Skylab, before NASA even existed, we already had blueprints for a city in space. Not a laboratory, not a capsule, a wheel, a spinning space station turning slowly in orbit, where gravity wasn't missing, it was manufactured. We never built it, but we could have, and one day soon, I think we will. The plan we almost followed. When we talk about space habitats on this channel, we usually begin with visionaries. John Desmond Bernal imagining a crystal sphere in 1929. Gerard K. O'Neill improved on his idea and began laying out orbital cities in the 1970s. We've explored those designs in detail before, from the Stanford Torus to the O'Neill cylinder and the Bernal sphere, and each represents a different step toward large-scale space settlement. But there was another design that came in between the dreamers and the megastructures. And unlike Bernal's philosophical essay or O'Neill's post-Apollo industrial vision, this one wasn't speculative futurism. It was a program proposal. In the early 1950s, long before Apollo, before Saturn V, before NASA itself, Wernher von Braun and his colleagues laid out a detailed roadmap for human expansion into space. It was published in a series of articles in Collier's, complete with engineering diagrams, launch schedules, and artwork that would reshape the public imagination for decades. The sequence was methodical. First, develop heavy lift rockets. Second, build a rotating space station. Third, use that station as a staging ground for lunar missions. Then Mars. The moon landing wasn't the beginning in that plan. It was step 3. Step 2 was the wheel. And it wasn't a toy model or a rough sketch. It was a serious engineering proposal for a permanent, crewed rotating space station in low Earth orbit, one designed not merely to visit space but to live there. What the von Braun wheel actually was. When people picture the von Braun station, they usually imagine the iconic artwork, a great spoked wheel floating against the black, sunlight glinting off its rim, or maybe the popular double wheel variant we first see in the epic movie 2001. But what was it really? The design most often cited was about 250 feet across, roughly 75 to 80 meters in diameter. That's small compared to the Stanford Torus, which measures over a mile across in its classic form, and tiny compared to the O'Neill cylinder, stretching 20 miles long. This was not an orbital city, it was a frontier outpost. The wheel consisted of a central hub connected by spokes to an outer ring. The ring rotated, generating artificial gravity along its rim. The hub remained effectively weightless, serving as a docking port and transfer point. Crew would arrive in spacecraft, dock at the center, move outward through the spokes into the rotating section, where centrifugal force would press their feet to the floor. The station was designed to host roughly 1,000 personnel, scientists, engineers, technicians, living and working in shifts. It was envisioned as a combination research laboratory, observatory, and military reconnaissance platform. Cold War realities were never far from 1950s planning. But its most important feature wasn't its mission, it was its rotation. This was humanity's first serious proposal to solve one of the fundamental problems of space habitation: gravity. Why spin at all? By the early 1950s, we didn't yet know that long-term weightlessness would cause bone density loss, muscle atrophy, cardiovascular weakening, and fluid redistribution. Those unpleasant discoveries would come later through Mercury, Gemini, Skylab, Mir, and ultimately the International Space Station. But even before we had medical data, engineers intuited something simple. Humans evolved in gravity. If you remove it, problems would follow. Von Braun's team did not want astronauts floating indefinitely. They wanted a station where crews could live in something approximating Earth normal conditions. Artificial gravity wasn't a luxury feature. It was considered a baseline infrastructure. And the physics is straightforward. Spin something a circle, and anything attached to it experiences outward acceleration, what we call centrifugal force. At the rim of the rotating structure, that acceleration can be tuned to match Earth gravity. In later habitat discussions like the Stanford Torus or O'Neill cylinder, we prefer large radii and slow rotation rates, 1 revolution per minute or less, to minimize Coriolis effects and motion sickness, with the intent of having families and nature there. The von Braun wheel didn't need or want that luxury. At only 75 meters in diameter, we would need to spin at roughly 3 revolutions per minute to generate Martian gravity, around 5 RPM to get near Earth gravity at the rim. It is fast enough that head movements could produce noticeable Coriolis effects, Pouring a drink, tossing a ball, or even turning your head quickly would feel subtly strange. But it was workable, and compared to total weightlessness, it was vastly preferable and less strange. In essence, the wheel was a compromise, not large enough to eliminate all rotational quirks, not small enough to ignore gravity entirely. Instead, it was the smallest practical step in artificial gravity. And it is what makes it historically profound, yes, but it is also what makes it useful to us in the near future. The road not taken. Now, here's where things get interesting. We did follow much of von Braun's roadmap, at least initially. Heavy lift rockets were developed, Saturn V flew, humans walked on the moon 6 times. In many respects, the technological arc he outlined came true. But the sequence inverted. Instead of building the rotating station first, we jumped directly to the lunar missions. We treated orbit as a transit zone rather than a destination. Skylab, Salyut, Mir, and the ISS were all non-rotating platforms. We chose microgravity, and we had good reason for that choice, too. Partly because it was simpler, and partly because it was cheaper in the short term. The political urgency of the space race prioritized flags and footprints over infrastructure. A rotating station was a long-term investment. A lunar landing was a geopolitical statement. But it was also, in many ways, a nod to scientific necessity. The early science we needed to conduct in space was largely about understanding how things behave differently in microgravity. Materials processing, fluid dynamics, combustion, crystal growth, human physiology. All of these demanded extended exposure to weightlessness. If we had built a rotating habitat, we would have needed axial extensions or tethered pods to conduct microgravity experiments. That would have been entirely feasible, and in fact would have made life easier for astronauts by giving them both low gravity and zero-G environments to compare. It would also have allowed us to study partial gravity, lunar and Martian levels, decades earlier than we are now seriously considering. But we also wanted clean, sustained data on how humans function in full microgravity. A non-rotating station, being cheaper and easier to build anyway, served that goal directly. There were discussions at various points about having rotating space stations or adding artificial gravity modules to the ISS, but they never materialized. A rotating station requires additional structural complexity, balancing rotating masses, managing gyroscopic effects, dealing with bearings or magnetic couplings, and ensuring dynamic stability over years of operation. Now, these are engineering challenges we were capable of solving. They're not strictly necessary for the short-duration missions that defined early spaceflight. When budgets are tight and timelines are political, not strictly necessary tends to mean not this decade. And so artificial gravity was deferred. It wasn't disproven. In fact, many people still seem to think spin gravity somehow doesn't really work, without realizing the very microgravity environment we experience in low Earth orbit is itself the result of rotation. Astronauts aboard a station only a few hundred miles up and are weightless because they are continuously falling around the Earth. They are centrifugal acceleration exactly balancing gravity. Spin gravity isn't speculative physics. It's the same principle in reverse, and what gets the water out of your clothes in the washer's spin cycle. And spin gravity certainly was not rendered obsolete. If anything, every year we've spent studying bone loss, muscle atrophy, fluid shifts, and radiation exposure has reinforced the original intuition that humans are not built for long-term weightlessness. We learned a great deal in microgravity. We also learned its limits. For over half a century, we have lived and worked in orbit without ever taking the next step. We've mastered weightlessness before we mastered gravity off Earth. We built laboratories, not settlements, transit points, not homes. But the longer our missions become, to the moon again, to Mars, deep space, the more that missing piece stands out. Gravity is not a luxury feature of civilization, it's a baseline infrastructure. And the moment we decide to install it in orbit, we will finally be picking up the thread that von Braun laid down in the 1950s. The wheel was never cancelled because it was impossible. It was postponed because it wasn't urgent. And that calculus may not hold for much longer. A log cabin in orbit. When we look at the broader evolution of space habitats, the von Braun wheel occupies a fascinating niche. The Bernosphere was a philosophical leap, a vision of permanent off-world living, especially in Berno's actual design, which was a bit strange. The Stanford Torus design is a community habitat. The O'Neill cylinder is an orbital state. The wheel was something else. It was a log cabin, small, self-contained, built with known materials, designed as that first foothold. It did not attempt to house millions. It did not try to optimize land-to-mass ratios. It did not require asteroid mining or graphene superlaminates. Rather, it required steel, aluminum, rockets, and political willpower. And in 1965 or 1975, it might have been within reach. Which raises a very uncomfortable question. If we could have built artificial gravity in orbit half a century ago, why haven't we built it yet? Could we build it today? If the Braun Wheel was premature in 1965, the more interesting question is whether it is overdue in 2026. Again, that original design called for a structure roughly 75 to 80 meters across or 250 feet. That's small by megastructure standards, but it's not small in engineering terms. Still, it is dramatically smaller than most rotating habitats we typically discuss here. The Stanford torus stretched over a mile and the O'Neill cylinder tens of miles. The wheel is closer in scale to modest sports stadiums than a city. And that matters. The International Space Station is about 420 metric tons. A von Braun-style rotating wheel habitat with modern materials, optimized structure, and modular components would likely fall in the same order of magnitude. Perhaps somewhat heavier if robust shielding were added, perhaps lighter if built for partial gravity, rather than full Earth normal load. But even if we double the ISS mass to account for structural reinforcement and redundancy, we are still talking about something that could be launched in pieces over a couple dozen heavy-lift flights, so yes, we can get that part done. That would have required a superpower scale mobilization in 1962. Today is a matter of logistics and sustained funding. With fully reusable heavy-lift vehicles like Starship, particularly in the 100-ton payload class, the launch problem becomes logistical rather than existential. Instead of requiring a decade-long national mobilization, the wheel becomes a multi-year construction project. Modular ring segments could be launched separately, assembled in orbit and gradually spun up. Docking hubs and central trusses could be built first, followed by outer habitation modules. We can already assemble large structures in orbit, the ISS proved that. What we have not done is to assemble a rotating one. The other big question, though, is whether or not we actually need one yet. One could argue that we are approaching the limits of what microgravity alone can teach us. If our long-term goal is human development in space, then we need environments where large populations can live under controlled gravity conditions in the long term, and we can systematically compare partial gravity to zero gravity. A fair counterpoint is the moon offers low gravity just fine. It's not that terribly far away. And that is a valid argument, though a debatable one, because lunar gravity cannot easily provide adjustable or comparative gravity environments in the way a rotating station can. It's adjustable for them, the gravity equivalent of a dimmer switch. The engineering challenges are serious, but they are bounded. A rotating station must manage angular momentum carefully. Docking events introduce torque imbalances. Mass distribution must remain symmetrical. Bearings, magnetic couplings, or counter-rotating systems must be used to isolate rotating sections from stationary hubs. But none of this requires unknown physics. It requires careful systems engineering instead. And compared to building a lunar base or sending a crewed mission to Mars, a 75-meter rotating wheel in low Earth orbit is kind of modest. In fact, it may be the most practical intermediate step for long-duration planetary missions. The missing link to Mars. If Mars is meant to be a destination rather than a stunt, then artificial gravity stops being a comfort feature and becomes a design constraint. A 6 to 9 month transit to Mars in microgravity exposes crew to extended bone loss, muscle atrophy, and cardiovascular deconditioning. Astronauts must exercise for hours each day simply to slow the deterioration, time they could otherwise have spent on training or other mission demands, and upon arrival they step into a gravity field that is only 38% of Earth's. We still do not know whether that level is sufficient to maintain long-term health over years, let alone decades. And a rotating station in Earth orbit would allow us to answer those questions before committing crews to multi-year interplanetary missions, and spending vast sums on them. A von Braun-style wheel could host long-duration partial gravity studies at Martian and lunar levels while maintaining full 1G comparison cohorts within the same structure. Instead of guessing whether 0.38 G is enough, we could test it continuously. Instead of discovering long-term physiological limits on Mars itself, we could identify and solve them in orbit, under controlled conditions, with help nearby and evacuation as an option. You could even use that station as the Mars transport ship itself if you liked, and we will talk about Aldrin cyclers in a bit. A Mars transport ship does not need to be a 20-mile cylinder. Indeed, it can be as simple as 2 habitat modules connected by a tether and spun for gravity, or as robust as a rigid ring with a central docking spine. Cargo can remain near the hub, living quarters at the rim, and rotation can be paused during burns and resumed during cruise. The first time a Mars-bound crew spends 6 months in steady artificial gravity during transit, the psychological shift will be as important as the physiological one. they would not be enduring weightlessness, they'd be living under installed gravity. And once that becomes standard practice, gravity in space is no longer theoretical, it becomes operational. Operational advantages beyond health. Artificial gravity does more than preserve bone density, it restores normality. In microgravity, even the simplest tasks require engineering solutions. Fluids must be pumped rather than poured. Tools drift unless tethered and are trickier to use, making mistakes more likely, potentially critical ones. Sleeping requires restraint systems. You essentially put yourself into a full-body sleeping bag and strap it to the wall, and often that comes after taking sleeping medication. Usage rates of sleeping pills in orbit are reportedly 10 times higher than the American average, which is already often considered very high. Showers are impractical. Toilets depend on airflow dynamics rather than plumbing. Exercise is not a lifestyle choice but a medical necessity. Even routine maintenance becomes a choreography of handholds and footholds. An alien environment is one where every piece of work takes longer and is more likely to fail. A rotating station quietly removes most of that friction. Water falls downward. Air circulates in layers rather than dispersing uniformly. Cooking resembles cooking, not rehydrating cardboard. Furniture stays where you put it. You stay on that furniture when you fall asleep. Plants orient themselves predictably toward light instead of spiraling in arbitrary directions. Processes that rely on sedimentation, convection, or material separation behave in familiar ways. What feels mundane on Earth is, in space, a dramatic simplification of operations. For orbital industry, that simplification matters. Imagine assembling large spacecraft structures, pressure vessels, or kilometer-scale trusses in an environment where workers can stand, brace, and use tools in ways their bodies evolved to use them. Humans are adaptable, but our ergonomics, our instincts, and our industrial tooling all assume gravity. A gravity-enabled workforce does not eliminate automation, it makes hybrid human-machine manufacturing way more efficient and way more intuitive, and thus cheaper and safer. A rotating station also becomes something more than a laboratory. Its hub can remain weightless, ideal for docking, cargo transfer, and delicate maneuvers, while its rim provides gravity for adaptation, fabrication, and heavy assembly. Crews can move between these environments as needed, shifting from zero-G work to stable gravity for extended operations. In that configuration, the station is not merely a habitat, it is a working harbor. Ships arrive in microgravity and depart from a port where life feels grounded, even while you're floating hundreds of miles up. As orbital transfer increases, such hybrid environments become not exotic but practical. Space settlement is simply unlikely to begin with 10-mile cylinders housing hundreds of thousands. It will begin with scaled-up operational infrastructure, a place where people can live, work, build, and expand without fighting their environment at every step. So the wheel is not just a health solution, it's a productivity multiplier. And it may start as a frontier outpost, but you can add a second wheel, a third wheel, etc., to let it be more of a growing town, if you need it, or you just add another wheel elsewhere, some other place you need to get work done, so you can grow as need demands, and not risk overbuilding. The evolutionary step between laboratory and settlement. Low Earth orbit today is an outpost. Crews rotate in and out. Missions are time-limited. Resupply is constant. The International Space Station was never meant to raise children or host permanent residents. It's a laboratory, optimized for research, not continuity. A rotating wheel represents something different. Not yet a city, but no longer merely a lab. It's hardly a luxurious environment, but you can start to really have off time and recreation. A day off to stay in bed and read, or a corner of the room you can hang a basketball hoop in. Some sort of green space to help you scrub your air of carbon dioxide and odors. The space station stinks. Ask any astronaut who's been there. They all have their stories about it. I'm always surprised anyone wants to do another tour of duty there. So design priorities can shift accordingly. Storage turns into housing. Expansion modules become neighborhoods. Docking hubs evolve into districts and ports. You've been planning for years, not months. Again, you can always add another wheel for another purpose, or even a non-rotating section. It is difficult to imagine a thriving, multi-generational orbital population confined indefinitely to microgravity. It is much easier to imagine a network of rotating stations forming the backbone of orbital civilization. And that network begins anywhere, it begins with something modest, something achievable. From wheel to network. The von Braun wheel is not an endpoint, it is a seed. Once you demonstrate that rotating habitats are operational, economically viable, and biologically sustainable, scaling is no longer philosophical and becomes engineering. Two wheels connected by tethers or a shaft become a larger complex. Multiple rings around a shared hub form modular habitats. Clusters of rotating stations become orbital towns. Larger rings evolve into tori. Extended axial structures evolve into cylinders. Every grand rotating habitat we discuss begins with the same physics: mass distributed at radius, spinning to simulate gravity. The wheel is the smallest coherent demonstration of that principle at settlement scale. You can go a bit smaller with tether and hammer habitat designs. In a mature spacefaring civilization, the largest megastructures will capture the imagination, but they will be rare. The most common structures will be smaller, modular, and replicable. A Stanford torus may function as a town, and O'Neill cylinder as a city-state, but the solar system will likely contain far more wheels than either. They are orbital equivalents of ships, ports, and frontier forts, numerous, adaptable, and economically realistic. Interplanetary craft. The most immediate application is spacecraft. We often picture deep space vessels as monolithic cylinders, but the simplest way to generate artificial gravity is to put mass at radius and spin it. Two habitat modules connected by tether already form a primitive rotating craft. Spin them and you have gravity, reel them in and you regain maneuverability, expand the radius and you reduce rotation rate. The geometry is unmistakably that of a wheel. A more durable interplanetary cruiser might use a rigid ring with a central docking spine. Cargo and propulsion remain near the hub. Living quarters occupy the rim. During major engine burns, rotation perhaps slows or pauses. During cruise, it resumes. You might even use inflatable sections, folding plates with balloon interiors that can fold in for heavy burns or radiation storms. For Mars transfers, asteroid expeditions, or out-of-planet missions, a 75 to 150 meter rotating section is vastly more practical than constructing full-scale ring or cylinder habitats. Once crews experience years of steady artificial gravity in transit, the idea of returning to prolonged microgravity will feel increasingly archaic, and I think improved efficiency and safety on board the ship will suddenly be beyond the additional costs. Now, consider interplanetary transport infrastructure like Aldrin cyclers, spacecraft placed in resonant orbits that repeatedly encounter Earth and Mars. A cycler is essentially a permanent interplanetary ferry. Crews rendezvous with it near Earth, ride it during cruise, and disembark near Mars. The vehicle itself never lands. It cycles endlessly between worlds. You take shuttles back and forth between those planets and the station, and those shuttles do not have to have vast amounts of radiation shielding, because you're only using them for a few hours. Nor do they need huge reserves of water and air, which can also act as radiation shielding, and those things are the vast majority of the mass for a ship besides its fuel. And the cycle itself does not use any fuel once it's actually been launched. So what is the ideal internal configuration for such a vessel? Almost certainly a rotating habitat. Cyclers operate for decades, even centuries. They are not short-haul vehicles. Crews and passengers may spend months or even years aboard. Artificial gravity dramatically improves long-term health, comfort, and productivity. A cycler built around a ring or multi-ring wheel design becomes not just transport but moving settlement. Restaurants, corridors, labs, and communal spaces exist under steady gravity, while the hub handles docking and transfer operations. And unlike O'Neill cylinders, which by sheer mass are often tied to specific orbits or Lagrange points, wheels on a cycler are mobile. Even ignoring that they're constantly moving between worlds, they can also be rededicated to different paths, so they are civilization in motion. If interplanetary travel becomes common, hundreds of such rotating vessels could exist across the inner solar system. Today we're looking at building rotating space stations, artificial gravity, and long-term habitats. Because once you leave Earth, you're not just visiting space, you are building environments that have to replace entire planets. And that idea is not unique to space. It shows up anywhere conditions are too harsh to live in directly. In my monthly exclusive, Surviving a New Ice Age, we explore how controlled, enclosed environments could let humanity endure extreme conditions, from deep deserts to frozen tundra, or even the dangerous depths of space. And if you enjoy the idea of megastructures as survival tools, check out Stuart Hicks' Nebula episode, Are Megastructures Really the Future? He looks at projects like The Line, a linear city designed to concentrate infrastructure, climate control, and transport into one continuous environment. Nebula is where every episode of SFA premieres early and ad-free, alongside years of exclusives and content from hundreds of creators. Right now, Nebula is offering 40% off a lifetime access, just $300 for permanent access to everything on the platform. Or you can use my link or the QR code to get 50% off an annual plan. Now that's just $30 for a whole year. Asteroid mining and industrial outposts. Now shift to asteroid mining. A mining outpost on a small asteroid does not need a 10-mile habitat, at least not at first. It needs something rugged, modular, and capable of keeping a crew healthy through long rotations. In many cases, the first habitat may simply be the ship that brought them there. Picture a year-long outbound journey in a rotating transit craft, a modest wheel providing gravity during cruise. When the crew arrives, they do not discard that structure, they simply repurpose it. The drive section is detached and dismantled. The reactor module is lowered into a crater for shielding and thermal stability. Then the rotating habitat ring is carefully lowered into another crater and set on a handful of narrow pylons anchored into the regolith. In near microgravity, those supports do not need to be massive. Even relatively light columns can carry the load. A thin dome, perhaps little more than an inflatable membrane, is deployed over the ring. Once sealed, crews pile a regolith over the dome in thick layers. In microgravity, you can stack enormous amounts of rock for radiation shielding with minimal structural stress. That same shielding helps protect you from micrometeors. Once that shielding is in place, the membrane can be even partially deflated or allowed to rest under the weight of the overburden. The wheel now spins protected inside its own armored bowl of stone in a relative vacuum to minimize friction and energy need to keep it spinning. The rest of the ship is cannibalized with purpose. Structural members become trusses. Tanks become storage silos or oxygen reservoirs as metal refining ramps up. Oxygen is a byproduct of metal production. Engine housing becomes machine bays. Very little is wasted. The interplanetary vehicle that carried them across space becomes the skeleton of the settlement. Outside the crater, additional work zones may be covered by inflated domes and buried in the same way. The base grows organically from what they brought with them. Small asteroids offer almost no gravity. Working on the surface requires anchoring lines, magnetic boots, and deliberate choreography. But the crews do not have to live that way full time. After a shift in near weightlessness, they return to the buried rotating ring for meals, maintenance, and sleep under steady artificial gravity. The wheel becomes the heart of the operation, not a grand city, but a practical residential core embedded in rock and attached to an industrial site. And because asteroid mining is likely to be decentralized, meaning modest claims scattered across the belt rather than a few colossal complexes, small rotating habitats make far more sense than monumental toroidal settlements. Long before we ever see a mile-wide Stanford torus rising over the asteroid belt or a 10-mile neocylinder, we may see dozens or hundreds of 50 to 200-meter wheels quietly turning inside shielded craters, each one a frontier town carved from stone and spin. The Infrastructure Multiplier. Space settlement will not begin with cities, it will begin with clusters. A group of families, researchers, or entrepreneurs does not need an neocylinder. They need something closer to an outpost or maritime town, compact, efficient, and expandable. A wheel 100 meters across, built as a multi-deck ring, already provides substantial living area. Add stacked interior levels, radiation shielding, and attached agricultural modules, and it becomes a visible small community. 2 wheels can be linked and counter-rotated for stability. 4 can share a docking spine, 10 can form an orbital village. Expansion does not require a civilization-scale leap. It requires another ring segment, another launch campaign. The incremental growth is the key. Megastructures demand centralized capital, political cohesion, and enormous industrial throughput. They are relatively rare by design, especially early on. We may build billions of them in the solar system alone one day, but we'll build far more of the smaller ones than bigger ones. A Stanford torus is a town, an neocylinder is a city-state. They are magnificent, and they will exist, but they are capital-intensive monuments. Wheels, by contrast, are easy to build and sell. Imagine a mature inner solar system with thousands of inhabited sites, research nodes, mining claims, cycler hubs, shipyards, logistic depots, private communities. Even if only a fraction use rotating habitats, the total number of wheels could easily reach into hundreds or thousands. Now consider scale. A single neocylinder might house 1 million people, but 1,150-meter wheels, each supporting a few hundred to a few thousand residents, depending on configuration, begin to rival or exceed that population aggregate. 10,000 modest rotating habitats distributed across orbital space, the asteroid belt, Mars orbit, and deep space trade routes could surpass the living area of a handful of megacities. On Earth, megacities capture our attention, but most people do not live in megacities, especially in earlier and developing eras and places. And even for those who do live in megacities, most do not live in skyscrapers. Cities might have 1,000 regular homes and townhouses for every skyscraper inside them. More people live in towns, suburbs, industrial districts, and regional ports. Civilization is not dominated numerically by its largest structures, it is sustained by its replicable ones. The same logic will apply in space. If we build 5 grand cylinders and 5,000 wheels, the skyline will belong to the cylinders, but civilization will belong to the wheels. And once rotation becomes normalized, the wheel geometry becomes the default template. It is the simplest durable way to provide gravity at scale without committing to megastructure economics. So in the future, the most common rotating habitat will not be the mile-wide torus or the 20-mile cylinder. It will be something close to the wheel, ranging in size from your basic von Braun up to your Stanford torus. For most folks, this is their future, not an O'Neill cylinder, let alone a massive bishop ring. Before we ever set foot on the moon, we had plans for a spinning station in orbit. We skipped it, and in doing so, we learned a tremendous amount about life and weightlessness. But the problem it was designed to solve, sustained, comfortable, gravity-enabled life beyond Earth, has only grown clearer with time. The von Braun wheel was not the ultimate habitat. It was the first practical one. And as humanity spreads through the solar system, it may not be remembered merely as a retro illustration from the 1950s. It may be remembered as the template for the most common building block of space civilization. Not the city, but the port. Not the monument, but the multiplier. When the history of space settlement is written, the great cylinders may headline the chapter, but the margins, the mining hubs, the cyclers, the orbital towns, the frontier outposts, the family farms will be filled with turning rings, and there may be far more of them than anyone first imagined.